Thank you for giving me the floor, Mr. President, and welcome everybody to my thesis defense on the centrifuge modeling of the installation mode of offshore wind turbine monopiles. As an outline of my thesis, I want to start by a general introduction of the topic. Then I show you three families of contributions, namely the technical development, including the experimental devices, test equipment and program, then the methodological and the numerical development. After that, I choose to present you the main results obtained during the framework of my PhD on three topics: the effect of the horizontal response of the monopile on first the impact driving installation, then the hammer frequency and fluid viscosity, and the last one is the embedding depth. Finally, I end my talk with the conclusions and perspectives. The marine renewable energy in France and around the world brings new challenges. One of them concerns fixed wind turbines that offers an economical solution when the seabed is beneath 35 meters. Generally, monopiles are today the preferred foundation solutions for offshore wind turbines. These monopiles are single, hollow steel tubes with a multi-metric diameter, often installed into the seabed by impact driving, using a hammer that tap on the monopile in order to drive it into the ground. For example, the first offshore wind farm is located not so far from here in France and is founded on monopiles and will be soon operational. Over their design service life, these monopiles are subjected to horizontal loads from the action of wind, wave, and current. So for the design of laterally loaded monopiles, offshore standards such as the MVGL has been developed. Based on soil reaction curves that represent the horizontal soil reaction P as a function of the horizontal pi displacement Y. These PY curves are obtained based on in-situ tests realized by Rees et al. 1975 on flexible and slender piles. It means with a length L to diameter D ratio very high. However, with the growth of the electricity production from the wind, the diameter of the monopile increased, and the slenderness ratio L over D decreased, resulting in a much stiffer behavior. And therefore, the conventional PY method is not adapted for large diameter monopiles for offshore wind turbines. Recently, within the framework of the PySoil analysis project, a significant improvement of the design method has been achieved. Additional soil reactions are incorporated other than the horizontal soil reaction P, including a shear forces that act along the shaft of the monopile and a shear and moment applied at the base of the monopile. However, to date, there are no standards for the design of large monopile for offshore wind turbines. This is why the objective of our study is first to better understand the horizontal response of large monopiles, not only globally, but also locally, means what's happening inside the soil, into saturated dense sand. And the main point is with the consideration of the impact driving installation, which is rarely considered in the literature. This is achieved by using the geotechnical centrifuge of the Eiffel University after developing a new experimental devices. And the geotechnical centrifuge is a tool very important in the field of geotechnics, since it allows to study the behavior of a real prototype structure on a 1/n reduced model subjected to a macrogravity of n times the Earth's gravity in order to really reproduce the stress state of the soil between the model and the prototype. The second objective of our thesis is to evaluate the performance of the design methods for laterally loaded monopiles in sand by comparing the experimental results with those obtained by the offshore DMVGL standards and the PISA approach. This is achieved by after encoding a one-dimensional finite element numerical model by using the Python language program. Let's move on to the three families of contributions and start by the technical development. Globally, two experimental devices are developed in the laboratory, including a saturation device on the left and a mechanical testing system on the right. They are validated from the Earth's gravity 1g, progressively in flight up to n times the Earth's gravity. Let's focus first on the saturation device. It's a system that enables to saturate the sand sample in flight and mainly with viscous fluid. Why viscous fluid? In order to reduce the time of the saturation process and to enhance the degree of saturation. How the system now works? This is a top view of the saturation system on the centrifuge. and a zoom on the fluid tank that is fixed at the base of the centrifuge basket. The idea is first to pour the fluid into the tank, and at 1G. Then, once the centrifuge acceleration reaches 60G, the metering pump that's rested at the base of the C strum box is activated in order to inject the fluid coming from the tank to saturate the sand into the S strum box. In addition, two vertical laser displacement transducers are positioned above the sand surface in order to verify that there is no settlement of the sand at the surface during the saturation. The system that is already developed for dynamic applications has been adapted now for our study, and it works appropriately until 60G. Moving to the second device, the main objective behind this construction is to combine in centrifuge first the installation of the monopile by impact driving using an electromechanical hammer maintained and controlled by a hydraulic actuator, and then the horizontal loading of the monopile from its head by using an electromechanical actuator, and all this without stopping the centrifuge in order to really maintain the surge state of the soil generated due to the installation process. This is a photo that on the right of the testing device implemented in the centrifuge basket. This system took about 8 pure weeks during my first year of PhD to be validated, and now it works appropriately until the maximum allowable centrifuge acceleration of 100G. I don't want to go deeply into the system, but just to give you an idea about the testing about the hammer. The principle of the hammer. It is based on a combined spin upward movement of the ram before its free fall. The hammer consists of 3 different pieces. The first one is the ram in the form of wing that around them are wrapped 2 diametrically opposed cylinder bearings, which are here in purple. The second piece in green is the support of the ram in the form of wave that on which are rested 2 cylinder bearing of the ram. And the final piece is the vertical fork that enables the vertical translation of the ram to up and down, and its rotation by using an electric actuator, motor. An anvil is also fixed above the head of the monopile in order to avoid damaging it at the moment of charge. So now, how this hammer works? There is a video taken at 1G that summarizes the hammering process. The idea is first to rotate the fork and therefore the ram, which will allow the free fall of the ram to a maximum height of 25 millimeters to hit the monopile, and then the move back up of the ram by rotation, and this continue as a loop until the monopile reach the desired depth. Now I show you a video that describes a typical test, including the monopile installation, then the horizontal loading without stopping the centrifuge at 100G. Initially, since the sample is submitted to the Earth's gravity, I increase the centrifuge acceleration during which the monopile penetrates a few millimeters into the sand. Then once I reach 100G, I start to install the monopile by impact driving using the hammer, by keeping the same hammering characteristics. And as observed, the number of blows, the monopile driving became less and less faster, and so the number of blows increased with the penetration depth. As shown here in this figure, representing the number of blows as a function of the normalized settlement of the monopile. And once the monopile reached the desired depth, I stopped driving it. Then I removed the vertical system in order to lateral load the monopile horizontally with a displacement control by pushing the steer rod that crosses the monopile through a fork that is attached to an electric actuator. And finally, I released the fork. After describing the experimental devices, it's time to talk about the model of strum boxes, sand, and monopiles used in the study. The soil sample is reconstituted by using the air privation technique into 2 different strum boxes. The C1 on the left is already used in the laboratory to conduct experiments on fire. However, the S strum box is relatively smaller and is designed during my PhD in order to saturate the sand mainly with viscous fluid and in flight. And as I am at scale and time, the sand into the S-tron box is saturated with instrumented with several pore pressure transducers located at different depths in order to measure the excess of pore fluid pressure generated during the installation of the monopod. A Fontainebleau sand of an average grain size of 0.21 millimeter is used in the study, and a relative density of 82 and 87% is obtained respectively for the strong box C and S, based on several calibrated boxes implemented close to the base of the monopod. The soil sample saturation is done in both cases by injecting the fluid through 4 draining channels located at the bottom of each strong box. The C1 is saturated by tap water at 1G, while the S1 is saturated in flight, mainly with the 60 CST viscosity fluid or by water. The viscous fluid is prepared in the laboratory at a temperature of 20 degrees Celsius by a mixture of the specific quantity of water, hydropropyl methylcellulose, and biocide. The degree of saturation is also estimated to be 96% for the strong box C and 94% for the strong box S. In the study, 2 model monopiles are used. They have exactly the same external diameter of 50 millimeter and a total length L of about 10 times the monopile diameter. In this table are shown the monopiles in the models, both monopiles in the model scale and in the corresponding prototype scale. The first model is the most used and is made of aluminum in order to respect the scale factor of flexural and actual rigidity, because as the model thickness is thicker than the monopiles used in field conditions. However, the second monopile is made of steel with the same characteristics as the first one, apart the wall thickness, which is thinner, in order to study the effect of the wall thickness during the installation on the horizontal response. And here are the longitudinal and transverse section of each model. They are instrumented similarly, with first a potentiometric displacement sensors fixed inside the monopile to measure the internal height of the soil column during installation, in order to verify that there is no soil plugging occurred. Secondly, with 2 horizontal laser displacement transducers fixed in front of the monopile in order to measure the horizontal displacement at 2 different elevations during the loading. And last but not least, each model is instrumented not this time with strain gauges, but with 2 identical diametrically opposed cylinder bearings fixed inside the thickness on the monopile cross sections in the loading direction. Within each fiber, several fiber Bragg rating sensors are implemented, each over the monopile length, each half a diameter from its base, in order to measure the external actual deformation of the monopile during its loading at different cross sections. Overall, 25 exploitable experiments are conducted in the study on centrifuge model, tested either at 60G or at 100G, into 9 different strong boxes, in order to study the effect on the horizontal response of the monopile of first the installation mode by using 2 different methods, jacking at 1G or impact driving at 100G. Secondly, the slenderness ratio tested between 3 and 5. Then the fluid viscosity tested for 1 or 60 CST viscous fluid, as well as the hammering frequency between 5 and 30 blows per second. Other parameters are also explored, but not sufficiently, such as the vertical load by varying the weight of the anvil fixed on the head of the monopile, the cyclic loading, and the horizontal loading rate. Let's move on to the second methodological development. Thanks to the instrumentation of the monopile, a new method is developed in the study to analyze to determine the local the monopile response globally, that represent at the ground level the horizontal load Hg as a function of the horizontal displacement Yg, and the bending moment Mg as a function of the neutral axis rotation of the monopile θg. But also locally, that represents the horizontal soil reaction P as a function of the horizontal pi displacement Y at different depths of in the soil. And here it is described the procedure of the method. First of all, after calibration of the optical fibers, the bending moment is calculated at different depths, at the depths of each fiber Bragg ratings, presented in a green dots. Then the bending moment profile is obtained by interpolating the measurements by using a polynomial of order 5, where the three first coefficients are determined from are obtained from the bending moment M and the shear force H, calculated at the level of the fiber Bragg rating position at the center face, and from the absence of the slow reaction P at the center face. And the remaining coefficients are obtained from a best fit of the measured data. So once the profile of the bending moment M is determined, on one hand, the profile of the slow reaction P is obtained by double differentiation of the moment MP due solely to the slow reaction P, which is deduced from the total moment M as described later. And on the other hand, the profile of the horizontal displacement Y is obtained by double integrating the profile of M by using this equation after modeling the monopile as a Timoshenko theory, with the two integration constants determined from the measurement of the higher laser and from the rotation center identified by using an incremental method developed by Lee. Therefore, at a specific depth Zi, I can obtain the value of P and Y corresponding to the first increment of loading. Similarly to the second, third, and nth increment of loading, in order to obtain the local PY response of the soil at a depth Zi. In the same manner, I can proceed to infer the global HG, YG, and MG theta G response. So now, how I can determine MP that is used to infer P? According to Birne et 2017, the total bending moment M along a large monopile is resulting not only from the moment MP, which is just due to the slow reaction P as for standard pile, but from a combination of the moment MP with the distributed moment small m that is due to the shear forces that act along the shaft of the monopile. Therefore, MP is obtained by subtracting the total moment M derived from the optical fiber measurement with the distributed moment small m assessed by the PISA approach, as it cannot be experimentally derived. However, M is a function of P, which is the purpose of this calculation. This is why for each loading state, an iterative process on P is developed in the study to determine the couple small m, small p, in order to infer the local and the global response of the monopile. At the first increment, at the first iteration, the bending moment M and the slow reaction is assumed null, as the monopile is considered at the rest initially. Therefore, MP is equal to M, and after conducting differentiation and integration procedures, the profile of the displacement, rotation, and the slow reactions are obtained along the length of the monopile. Then, for the remaining iteration number bigger than 1, the distributed moment M is considered and is determined from the experimental variables obtained at the I-1 iteration. Then I continue to repeat the same process until the norm of the difference between the slow reaction at the iteration I and I-1, normalized by the norm of the slow reaction at the iteration I-1, is lower than a tolerance value, which is chosen to be 10 to the power minus 2, based on a convergence criteria. That's and finally, a final contribution, a one-dimensional finite element model is encoded in order to compare the experimental results with those obtained by the PISA method. The 1D approach is based on a generalized Winkler model, where the monopile is modeled as a Timoshenko beam with a horizontal load HG and a bending moment MG applied at the ground surface, and the surrounding soil by sets of nonlinear springs in translation and in rotation, with four different components that are modeled as a dimensionless conical functions. Here it is the equation and the shape of these functions, each one of 4 parameters, some of which depend on the depth. The first parameter K identify the initial slope of the curves. Sigma bar U and epsilon bar U represent the ultimate value of the slow reactions, and the normalized displacement or reaction, the corresponding normalized displacement or rotation. And the final parameter N identifies the shape of the transition from a high initial stiffness to a more flexible nonlinear response. Now the foundation of our study is built. I can move on to the results. As I said, I choose to present you just 3 thematics. the effect on the horizontal response of the monopile of first the impact driving installation, then the Hammer frequency and fluid viscosity, and finally the embedding depth. The impact of driving the monopile on the horizontal response is still neither well understood nor quantified in the literature. This is why a couple of horizontal monotonic tests are conducted at 100G. With the first one is installed exactly similarly. With the first one is installed by impact driving at 100G, and the second one by jacking at 1G. The reference test, so-called the G1G, by comparison of the ID100G test, enables to quantify the impact of driving the monopile on the horizontal response. First of all, I present you for the monopile one with a prototype diameter of 5 meters, installed down to 5D into water-saturated dense sand by using both installation methods, the global response of the monopile in prototype scale that represents mg and hg as a function of theta g and the normalized displacement yg over t. Both tests show monotonically increasing evolution of the lateral resistance, with the ID100G test resist better to overturning moment and lateral load than the G1G test. Also, on these figures are plotted the improvement delta brought by the impact driving installation that represents the normalized the resistance of the difference of the resistance between both tests, normalized by the lateral resistance of the G1G test. And it shows two different phases separated by A' lines. During the first phase of loading, this improvement delta is much more pronounced. Then it tends to decrease progressively until stabilization for high loading amplitudes. In order to better understand this trend, it's necessary to focus on what's happening inside the soil. And here it is, the local response of the monopile for both installation methods and at different depths every 0.5. For small loading amplitudes, the Py over D curve for the ID100G test, which is presented in red, are stiffer than those obtained for the G1G test. Then, with the increasing of the loading, this increase is less pronounced, and for Z equals 0.5D, both tests show attain similar plateau. So the increase of the horizontal of the initial of the stiffness for the ID100G test can be explained by an increase of the horizontal stresses generated along the shaft of the monopile during its installation by impact driving, compared to the case observed during the installation as a wish-in-place monopile. However, this increase of the radial stresses is localized in a zone close to the monopile. This is why, for high loading amplitudes, mobilizing the soil far away, the difference of the soil reaction between both tests is decreased. The results are quantified based on two different criteria. The first one, theta G equal to 0.5 degree, close to the service limit state of a typical offshore wind turbines. And the second one, Y equals 0.1 D, that represent the ultimate limit state for large displacement amplitudes. I present you the sequence stiffness for theta G equal to 0.5 degree in the table on the left, and in the table on the right, the lateral resistance at Y equals 0.1 for both tests. The results claim that the impact driving installation improved the sequence stiffness about 3 times than the jacking than the wish-in-place installation. And for high displacement amplitude, the lateral resistance is just increased by about 1.3 times. To evaluate the performance of the DMVGL offshore standards, the DMVGL, the experimental PY curves are for both tests are compared with the DMVGL standards presented as a dash lines in terms of sequence stiffness at theta G equal to 0.5 degree and lateral resistance at Y equals 0.1 G. For the G1G test, the DMVGL predicted stiffness values 2.6 to 5.8 times greater than the experimental ones. However, for the ID100G test, the DMVGL values are 1.2 to 2.8 times greater. Therefore, I can conclude that the experimental results remain smoother than those obtained by the DMVGL standards. However, with impact driving the monopile, the response are the experimental results are much more closer to. And for high displacement amplitudes, the experimental result lateral resistance are almost similar to those obtained for standard. The impact of driving the monopile is also explored for different wall thicknesses. It's achieved by comparing the improvement delta brought by the impact driving installation between both monopiles installed with two different wall thicknesses. The improvement is much more pronounced for the first model. At a rotation of 0.5 degree, this improvement is equal to 61% for the monopile 1, which is slightly greater than 54% for the monopile 2, which is thinner. This may be due to the larger sand displacement volume obtained during the installation of the thicker monopile, which leads to a greater horizontal stasis generated along the shaft of the thicker monopile. Finally, on the first thematic, the first thematic is also explored by using different embedding depths, but solely on the second monopile. Here it is at a different standardness ratio of 5 in red, 4 in green, and 3 in blue. The global mg theta g response of the monopile for both installation methods, and the improvement delta brought by the impact driving installation for each case. The results obtained are almost similar to those obtained on the first model. At the lateral resistance of the IG100G test is always greater than the G1G, and the improvement delta is much greater for small displacement for small loading amplitudes, but also for low length to diameter ratio. At a rotation of 0.5 degree, this improvement delta increased from 54% to 92%. It means which is about 1.7 times greater, as L over D decreased from 5 to 6. So from this first thematics, it must keep in mind that the impact driving installation should be accounted in the design of laterally loaded monopiles, with a degree of improvement much more pronounced for a smaller length to diameter ratio and a lower length to diameter thickness ratio. The question is now why I studied the second thematic on the impact of hammer frequency and fluid viscosity on the horizontal response. In order to investigate the impact of driving the monopile and centrifuge at NG on the horizontal response, the model needs to be installed with a higher hammerable rate of about n times the prototype one. That corresponds to about 0.5 to 0.6 blows per second in the prototype, and into soil that is saturated with a NCST viscosity group. The reason of this is to avoid the conflict between of the scaling relating to the dissipation of the excess of water pressure and those relating to dynamic phenomena occurred during the installation of the model. However, in the literature, this has not been achieved. This is why this thematic is studied after conducting 6 experiments, this time at 60 G, on the monopile 1, installed with different blow rates of 5, 20, and 30 blows per second, and then horizontally tested into dense sand saturated either with water or with 60 CST viscosity fluid. I want to start by the impact of hammer frequency and present you the pore pressure for several pore pressure transducers located at the different depths that from the ground surface and different radial distance r from the monopile center. The excess of pore fluid pressure delta U normalized by the initial vertical effective stress sigma prime V as a function of the model type. During the installation of the monopile into viscous fluid saturated with dense sand, on the left with the highest hammer frequency of 30 blows per second, and on the right with the lowest hammer frequency of 5 blows per second. In addition, the time at which the monopile reached 1D, 2D progressively up to the final depth 5D is also noticed. Both tests show exactly similar response. Higher pressure excess of pore fluid pressure values are obtained for shallower depths until Z equal 1D, due to the higher penetration rate of the monopile initially. Then it tends to decrease progressively between 2D as the monopile progresses between 2D and 3D, until reaching smaller values after 20 and 47 seconds respectively from the start of the time. The maximum peak attenuated for the transducers are almost similar for both tests, and there are very low with respect to one, Therefore, there is no liquefactions that are observed at the sensor zone during the installation of the monopile into viscous fluid saturated with dense sand, even with the higher hammer frequency. The global response of the monopile is examined for different for monopile tests with different hammer frequency into viscous fluid on the left and water fluid on the right. Overall, the global response of the monopile is independent of the hammer frequency for both fluid viscosities. This may be due to the this is confirmed by the pore pressure transducer measurement, as almost similar profiles are obtained for the extreme hammer frequency. The impact of the fluid viscosity is also studied by comparing two tests conducted with the highest frequencies that corresponds to a realistic field scenario, and but with the dense sand saturated either with the 60 CST viscosity fluid in green, or with water fluid or 1 CST viscosity fluid in blue. The normalized excess of pore fluid pressure is obtained plotted for both fluid viscosities. The higher pressure profiles are obtained for the viscous in the case of viscous fluid than in the case of water fluid. Even for pore pressure transducer located close to sand surface in the case of water fluid saturation. Also, the driving curves are also presented for both tests that represent the number of flows as a function of the normalized settlement of the monopile. And it is obtained that the driving curve is much more easier into viscous fluid than into water fluid. The global and local response of the monopile is explored for both tests. It appears that the horizontal performance of the monopile is looser for a higher viscosity fluid. This may be due to the higher pressure profiles obtained during the installation of the monopile in viscous fluid than into the case of water fluid, which leads to a higher reduction of the horizontal stresses generated along the shaft of the monopile during its installation into viscous fluid. So from this second thematic, it must appear that the excess of pore fluid pressure may influence the horizontal response of the monopile, but not sufficiently into dense saturated sand. The final thematic is concerns the impact of the embedding depth on the horizontal response. 3 horizontal tests are conducted by installing the monopile with the impact driving into water saturated dense sand, down to 5D in red, 4D in green, and 3D in blue, in order to first improve the understanding of the impact of embedding depth on the horizontal response. Second, to compare the experimental results with those obtained by the one-dimensional finite element model, by considering all the soil reactions that are explored in the PISA project, in order to really evaluate the performance of the PISA approach. And finally, to assess the usefulness of the new developed analysis. In these figures are presented the global response of the monopile for the 3 different tests, experimentally in a continuous line and numerically in dashed lines. For standard, the response is obtained. It's very better for the standard pi, and the results obtained from the impact from the numerical analysis correspond very well to those derived from the experiment on impact-driven monopiles. In addition, I present you the rotation displacement response at the ground level for the 3 different tests. For the case of L over D equal to 3, the response tends to be linear, suggesting a pure rotation of the monopile. Then this linearity tends to decrease progressively as L over D increase, inducing, in addition to the rotation, more fracture. The local response of the monopile is presented as dimensionless P bar Y bar curves for the experimentally and numerically for the 3 different tests at a selected depth every 0.5 T. Experimentally, whatever the embedding depth is, 2 different trends are obtained. for small loading amplitudes, P bar increases progressively with Y bar, then it tends to decreases without reaching a plateau for high displacement amplitudes. The numerical response captures the first trend. However, during the second phase, a plateau is reached in the numerical model. Concerning the comparison between the experiments and the numerical results, for shallower depths, the numerical response is softer than the experimental ones. However, at deeper depths, the behavior is reversed. This is why, in contrast to the global response, the local response doesn't match reasonably well between the experiment and the numerical results derived from the PISA approach. On the last thematic, I want to explain the importance of the consideration of the new analysis method. But before, a small recap about this method. It's based on a iterative process in order to, by considering the distributed moment small m apart from the total moment m, to determine the Sohr reaction moment mp in order to deduce the Sohr reaction p. Distributed moment mp and the Sohr reaction moment mp and the corresponding distributed moment m is explored for the three different tests below the ground level at different loading states. We can see clearly that the values of m are respectively very low with respect to mp, and for supersymmetric state at a depth of the maximum mp, the ratio between m over mp is equal to 1.2, 1.4, and 2.1%. For the case of L over G equal to 5, 4, and 3 respectively. Therefore, I can conclude from these results that the distributed moment m are very low with respect to mp. However, it's much more pronounced for a low embedding density. And we all wondered why I considered the effect of m. Why I considered the value of m if its effect is very negligible with respect to mp. To answer to this question, here I present you the local P bar Y bar response of the soil for the three different tests obtained at a specific depth z equal 1.5 d, for without considering the consideration of the distributed moment m. It means m equal to 0. The results, whatever the embedding depth is, the results are almost similar for the three different tests. However, with the consideration of the distributed moment m, the softer response is obtained as L over D decreased with the mass difference obtained for the shortest file. In this table is shown, summarized the quantification of the sequence stiffnesses at theta g equal to 0.5 degree for both experimental methods. This the sequence stiffness for the case where m equal to 0 are 2, 5, and 26% greater than for the case of m different to 0 for L equal to 5d, 4d, and 3d respectively. Therefore, it is highly recommended to consider the distributed moment m to determine the Sohr reaction p, especially for low length to diameter ratio, and also the values of m are very low with respect to m. And this is it's already confirmed numerically, as the normalized ultimate Sohr reaction are decreased with the standard mass ratio L over D, but in a less pronounced way. Let's move on to the conclusions and perspectives. This study evaluated the horizontal response of impact driving monopiles in saturated sand after conducting 3 contributions. Technically, a new experimental devices is developed, including in-flight saturation system and monopile driver. Then methodologically, a new method is developed to advance the process of the determination of the experimental PY response. And finally, a one-dimensional finite element numerical model is encoded to evaluate the performance of the PISA approach. Developing these aspects needs time, ingenuity, and validation. However, important conclusions are drawn. First of all, the impact of impact driving the monopile needs to be accounted for in the design of laterally loaded monopiles, especially for small loading amplitudes, for monopiles installed with smaller length to diameter ratio and higher thickness to diameter ratio. Secondly, it must appear that excess of fluid pressure may influence the horizontal response of the monopile, but not in a pronounced way in saturated sand. It must keep in mind that as L over D enhanced from 3 to 5, the monopile behaves from a pure rotation to a rotation flexure response, with a less pronounced linear behavior, linear rotation displacement behavior at the ground level. As an important conclusion, the new developed experimental analysis method is very useful to determine the experimental local response of the local PY curves for laterally loaded monopiles tested in centrifuge, but also for institute tests, especially for low length to diameter ratio. Comparing regarding the comparison between the experiments and the MVGL standards, the experimental results remained softer than those obtained by the standard. However, with impact driving the monopiles, the results are much more closer to them. And finally, the PISA approach captures reasonably well the response obtained for laterally loaded monopiles in centrifuge for impact driving monopiles, for the global behavior, even if it is less accurate for the local behavior. As a recommendation for future works, it must also study the horizontal response into the horizontal response of the monopile into looser saturated sand, and by conducting a parametric study on the harmonic frequency and fluid viscosity, in order to study the effect of fluid viscosity on the behavior in question. Secondly, the offshore environment is cyclic in nature. Therefore, it would be interesting to quantify the effect of the impact driving installation on the variation of the foundation stiffness and accumulation of rotation displacement. In addition, the new quieter and faster vibro diving technique is now attracting very interest in for the offshore industry. Therefore, it would be worthwhile to quantify the impact of the installation on the horizontal behavior. And finally, developing a 3D FEM model with the consideration of the impact driving installation should be a direction to quantify, to better understand and quantify the horizontal response of today's large monopiles of about 10 meters in diameter. Within this thesis, 3 journal papers are written. The first one is already published in 2021 in the journal EGPMG. The second one is accepted in Geotechnique. And the last one is recently submitted to IGPMG. Thank you for your attention. And I want to thank the University Gustave Eiffel, the Région Pays de la Loire, l'Agence Nationale de Recherche, France Énergie Marine, and WIMEC for their financial support for this work. And last but not least, thanks for my supervisors for their continuous support and guidance to achieve